So we have seen first a very general one, which is the first one, which was convection diffusion reaction systems. In that block, we have seen that we could fit the Stokes problem and the Navier-Stokes equations as well, the linearized Navier-Stokes equations. Then we have analyzed the Stokes problem in more detail. That was the second block. And finally, we will see how to approximate the incompressible Navier-Stokes equations. So this block has three main parts. So the first one is the general theory about the problem and the Galerkin finite element approximation to it. Then the second one is devoted to the stabilization in the variational multiscale framework that we have seen. And then there is a last part which is not directly related to variational multiscale, but it's crucial to integrate in time the incompressible Navier-Stokes equations. And I will also explain it a little bit, just that you have an idea about what fractional step schemes are. Okay, so let's start with the Galerkin finite element approximation of the incompressible Navier-Stokes equations. So this first block has these points. The first one is in this case it's important because the Navier-Stokes equations are a very important problem, as you know. We will let's say consider in some detail the statement of the problem. So this is not just write down the equations, but seeing also the properties of those equations. And then so that will take us a while. Then we will go to the discretization in time. So we will forget about time. The weak form of the problem, I will also spend some time to obtain the weak form. The linearization of the convective term, that's another ingredient that we need to approximate the incompressible Navier-Stokes equations. It's the first nonlinear problem that we see. I mean, convection diffusion, the convection diffusion systems that we have seen are linear, and the Stokes problem is linear. So now this is a nonlinear problem. We will see the linearization. And then the finite element approximation using first the Galerkin method. So this is the first block of this chapter, and then later we will see how to use stabilized finite element methods to that, which will be easy. Okay. Okay. So let's start. No, I don't have. Let's state the problem. So the problem we want to solve is this one. The incompressible Navier-Stokes equations are those equations that you see here. So we want now we have also a time-dependent problem. Okay. So t is the time, 0t is the time interval in which we want to compute the flow. Omega is the spatial domain, and as before, u is the velocity, p is the pressure, and nu is the kinematic viscosity, and here everything is divided by the density, and those are the equations that we have to solve. Okay, so which is the structure of these equations? First, the structure is concerning the equations and unknowns is similar to that of the Stokes problem. So those two terms plus that continuity equation corresponds to the Stokes problem. But we have two additional terms. One is a nonlinear term that is nonlinear. It is quadratic in terms of the velocity, as you see. It's u gradient of u velocity gradient of velocity. And then we have also the time derivative of the velocity. So this is an initial and boundary value problem. Okay, so we have evolution in time. And since we have evolution in time, we need not only boundary conditions on the boundary of the computational domain, but also initial conditions at time t equal to 0. Okay, so that is the problem. As it said here, u and p are velocity and pressure, which are the unknowns. F, the right-hand side, the body forces, and the u naught, which is the initial condition, are data, and nu is the viscosity, which is a physical parameter. Okay, it's the only physical parameter that intervenes in the problem because the density is dividing everything. In fact, the original equations, when you derive them from the conservation equations of continuum mechanics, have a density here, the dynamic viscosity, the so-called dynamic viscosity mu here, and here a density. And the pressure is not that pressure, but the pressure divided by the density. Okay, this is sometimes called kinematic pressure. So those are the equations, beautiful equations that we have to solve. Okay, good. So which is the functional setting of the problem? That requires a little bit of explanation. And and maybe I'll do that in some detail, because this is related to the weak form of the problem. Later we will obtain that weak form in some detail, but first let's do just a simple weak form. So we have the following equations: du dt plus u gradient of u minus nu Laplacian of u plus gradient of p equals f, and divergence of u equals 0. Okay, so this is the problem that we want to solve. So what we will do to obtain the weak form: u is a velocity, is a vector, p is a scalar. So we multiply this equation, the first equation, by b and integrate, and we multiply the second equation by q and integrate over the domain. Okay, so that's what we do. What do we get? It's easy. What we will get is the following: integral over omega of b time derivative dot. This is scalar product because this is a vector. Time derivative of u. By the way, I used this notation for the time derivative. It is obvious. Plus the integral over omega of b dot u dot gradient of u. So this is a tensor. This is a vector. So this is a vector, and I take the dot product of this vector with this one. Then that term can be integrated by parts, as we did for the Stokes problem. So I don't need to work much on that. So that is going to be the gradient of b colon the gradient of u. Colon means double contraction. So both indexes of gradient of b are contracted with both indexes of gradient of u. Then minus integral over omega of b divergence of b equals to integral over omega of b dot f. Okay? So this is the weak form of the first equation. And then the second one, of course, we don't have any special thing. It's just this one. And that has to hold for all appropriate test functions v and all appropriate test functions q. Okay? So which is the a space where our unknowns have to belong? Which are the spaces into which our unknowns have to belong? Well, first, that equation holds for all time. For all time. I mean, for all time in the time interval, of course. And the first point is that it has to be understood almost everywhere in time. So that is the classical way to understand the equations. Okay, so this is a function equal to a function, but that doesn't need to be equal pointwise, but just in a measure sense, so almost everywhere. Okay, that's the first point. So we can, given a time t, we can multiply that equation by the test function v. So the first point is that velocity will be a function of position and time, and likewise pressure will be a function of position and time, but the velocity test function will be only a function of position. It is also possible to design space-time variational forms, but the most classical one is the one I will do now, which is to take the test function for velocity and pressure, just functions of position, okay? Just functions, just defined in the computational domain omega, just functions of position x. Okay, not of time. That's the first point. Now, for each time, let's fix time for the moment. For each time, which is the regularity that we need? Okay, for each time, for t fixed, it is clear that we need the same as for the Stokes problem at least, right? So we need the velocity, the test functions to be, and the unknown to be in h1, all the components, so we are in d dimensions, and pressure, the pressure has to be in L2, modulo constants. Okay, this is the same as we had for the Stokes problem, so I think it doesn't need much explanation. Why? Because we have this term, and this one, okay? Well, now the first question that arises is this term well defined? Is this term well defined? This is not obvious. That is not obvious. Why not? Because we have to make sure that this is bounded. This is bounded. We know that the gradient of u, since u belongs to h1, the gradient of u is an L2 function, because u is h1, therefore the gradient is L2. However, this gradient, which belongs to L2, is tested against a function which is not only u, but u times v. So what do we have to make sure that this term is bounded? V times U has to be where? In L2. So V times U has to be in L2. The product has to be in L2. And therefore, each of these has to be where? So I have a function that is the product, this function, which is the product of two functions, and the product has to be in L2. I mean, there are many combinations, but if they belong to the same space, which space should that be? Which one? What? Let me do the calculation on the other side. So I want a function, let me say fg, that belongs to L2. What does it mean that fg belongs to L2? Fg belongs to L2 means that the integral over omega of f squared g squared is bounded. That's what it means. But how can I guarantee that this is bounded? I can guarantee that this is bounded, for example, using Schwarz inequality. That is the square root of the integral over omega of f squared squared times the square root of the integral over omega of g squared squared. You see? So to guarantee that f and g belong to L2, I need that what? F and g belong independently to where? L4. F and g have to belong to L4. I mean, of course, there are different combinations, but if the space is the same, then it's L4. I mean, that could be, I don't know, 6 and 1 or whatever, you know, there are different combinations, but if the space is the same, it should be L4. So now we are, we have a little problem. If we have a function v and u that belongs to H1, we know that v and u belong to H1, then can we guarantee that v and u belong to L4? Can we guarantee that they belong to L4? Well, that's not a trivial question, but the answer is yes. Does anybody know which is the result that states this? Which allows us to guarantee that the function that belongs to H1 is an L4 function. Well, this is called, I don't know if they know, do they know that or not? No. This is called Sobolev's embedding theorem. Well, this is one case of Sobolev's embedding theorem. Okay, this is one case of Sobolev's embedding theorem. What does Sobolev's embedding theorem say? You know that the Sobolev spaces are usually written WMP, and M, that means that derivatives of order up to M, belong to LP. Derivatives of order up to M belong to LP. If you increase M, you get a smaller space, you get more regularity. If you increase P, you get a smaller space, you get more regularity. But the problem is, how do you compare spaces in which, for example, M increases but P decreases? Okay, so that is not trivial, you know. For example, the question is, I mean, between H1 and L4. In H1, you know that H1 is exactly the same as W12. Okay, so derivatives of order 1 belong to L2. And L4 is exactly the same as W04. W04. Okay, so the question is, here this space has more derivatives regular than this one. Here is 1 and here is 0. But they are only up to L2 square they belong only to L2, and here they have to belong to L4. So how do these spaces compare? You understand the problem? So it's not a trivial problem. And one of the results of one of the very particular cases of Sobolev's embedding theorem is that that space is included in this. Excuse me. That the space is included in this one. Okay. So if I have a function that belongs to H1, then it automatically belongs to L4. In fact, in 2D, it can be shown to belong to L6, but what matters is that it belongs at least to L4. Is it clear? So what is this comment for? This comment is to understand Now let's summarize that. That since V and U belong to H1 in all dimensions, they belong to L4 in all dimensions, and therefore the term integral over omega of V dot U dot gradient of U is bounded. It's well defined. Okay, that's the conclusion. Have you understood more or less the argument? So it was not trivial. It was not trivial to say that that term is bounded. Is well defined. So, by the way, let me make a parenthesis. Many people write the convective term as the scalar product of B U dot gradient of U. I have done it sometimes, but I don't like that. Why I don't like this? Because this is not the L2 product. It's not the L2. It's the integral, but it's not the L2 product. You understand the difference? The L2 product assumes that this function belongs to L2 and this function belongs to L2. This is what the L2 product, the inner product, assumes. But this is not true. I mean, the integral is well defined, but the arguments do not belong to L2. So fortunately, they belong to L4, and this one belongs to whatever, the dual of L4. I mean, it makes it integral. You understand the point? So that integral is well defined, but you cannot write it. I mean, you can, but it's not correct to write it as the L2 product of B times U grad U. Okay. Well, was just a comment. Perfect. So this term is okay because of this. This term is okay. This term now we have seen that is okay. As exactly as for the Stokes problem, we just need F to belong to H minus 1. So F needs to be less regular than L2 because V is in H1. And what about this term? Well, this term is easy because if omega is, well, that term is easy because if omega is constant, so the time domain doesn't change, and since V does not depend on time, this term is simply the integral over omega of B dot time derivative of U is the derivative of the integral over omega of B dot U, okay? Because omega is fixed in time and V does not depend on time. And of course, these two functions, this belongs to L2 and this belongs to L2, in fact more than L2, but at least L2, and therefore this term is well defined. This term is well defined. Okay, the problem is to take the derivative, but I am supposing T fixed. So concerning time, we are done. By the way, concerning time, we only require U and V to be in L2 to have that integral well defined. Okay? Good. Now it comes the point where we have to decide. That word is important. We decide in which sense do we want to understand this equation. Which is the consequence of that? I mean, we may decide whatever, but if our choice is not reasonable, we will not find a solution. You understand? So the idea of all partial differential equations is that you decide the space where you want to work. It's up to you. H1, H minus 1, L2. So I could understand that equation, any equation, the Navier-Stokes equations in L infinity or in C infinity. I could understand the equations in C infinity. The problem would be that I wouldn't find solutions in that space, in such a small space. You understand the problem? So you have to choose the space first that everything makes sense, so that everything is bounded. That is for sure. That is the first point. Everything has to be defined. Otherwise, I don't play the game. If some of the terms are infinity, I don't play. But once I have chosen a space that makes all terms well defined, I have to make sure that there exists a solution, so that the choice of my space is not arbitrary. Okay. Good. So now let's see in which sense do we want to understand this equation in time now. Well, there are several choices, and in fact, in that case, there are several choices that can be applied. But the most usual one is to understand this equation in L2. What does that mean? It means that, you see, this is going to be a function of time, because I integrate in a space, but I am leaving time free. So this is equation in time, okay? So where are we going to understand this equation in time? So we have a function equal to another function. Time-dependent function equal to another time-dependent function. In which space do we take these functions? In L2. We will see that in L2 is the appropriate space because it's very likely that there exists a solution. Okay? So, let's continue with our argument. We want to understand the equations in L2. We want to understand the equation in L2 in time. The equations in L2 in time. Therefore, which is the regularity that I need? If I look at these terms, I have seen that having the functions h1 in a space is enough. So their h1 norm has to be bounded in a space. And once this is guaranteed, I have to guarantee that it's L2 in time. Okay? So let me summarize it. We set the variational equation in L2 in time. In L2 in time. We set the variation in L2 in time. Therefore, we need to have U to belong to L2 in time, but what has to be L2 in time is H1 norm. Therefore, the space is written in this way. Okay? The space is written because it is a function H1 in a space whose H1 norm is L2 in time. Okay, this is what is represented here. The space LP in time. The way to read this space is functions which are LP in time with values. This is the way this is read. L2 in time with values in X, where X is a certain functional space that in this case is H1. So it's the set of functions from that map the time interval to the function space such that the integral, the P norm in time of the X norm in a space is bounded. Okay? So this is space LP in time of functions in space X. Is that clear so far? Any question? What about pressure? Pressure has to be L2 in time with values in L2 in space modulo constants. Well, that, by the way, sometimes this space is called L2 omega 0. That's a shorthand notation for what I said. Okay? Good. Good. So, now that we have this, how do we give meaning to the first term? Oh, the first term is more involved. Because we have a function in space that we integrate, and that depends only in time, and we have to take the derivative of that, and that the derivative has to make sense. This is more elaborated. That is some measure theory is needed to understand that. Not much, but a little bit. But in fact, it turns that if you to have that term well defined, the derivative of the integral over u and v well defined, that has to be an L infinity function in time. Okay, a bounded function. L infinity, you know, that means that the set of functions whose norm, whose supremum norm or max norm is bounded. Okay, the supremum norm is the or the essential supremum. I mean, you have to take out sets of zero measure, and then take the supremum over what is remaining. It's the maximum. Think of this as maximum. So it turns out that if this is L infinity, this is well defined. Is this well?
H1 functions are L4?
No, in space.
No, so isn't it that we should write H1 omega intersection L4?
Yes, but at least it has to belong to this space also.
Intersection of that.
Yes, that's what is written there, up there. Yes, but at least to that space. I'm going to argue that I have to add an additional condition. Okay, so we have to have this function L infinity in time. But fortunately, here we have more regularity required than here. Here we only needed L2. Now we have more regularity in time required because we have to take the derivative. You know, since we have to take the derivative, we have more regularity required in time. However, you know, we only have the scalar product of the function, not of the derivative. And for that function to be bounded, the only thing we need is that u and v here belong to L2. That's the only thing we need for this term to be well defined. You understand? Therefore, we need that the L2, the L infinity norm in time of the L2 norm in space of B, of U, be bounded. You understand that? So, we need only U, its L2 norm being L infinity. So, only the L2 part of U has to be in L infinity. Okay? Do you understand? So, those spaces cannot be compared, this one and this one. And since we have this condition and this one, U altogether has to belong to the intersection of those two spaces. And see what happens. See what happens. Those two spaces cannot be compared. Let me erase that. Those spaces cannot be compared because here we have more regularity in space than here, but here we have less regularity in time than here. You understand? So you could think of it as the following. You have a large space, which is L2 in space. A smaller space, which is H1 in space. But now we have time, which is, let's say, another axis, if you want to say. In that axis, we need of those functions that are H1, we have to take those that are L2 in space. L2 in space, which is less than what we need for the time regularity of the functions that are L2 in space. So, you know, you cannot compare both spaces. And that's why you have to take the intersection of both. At the end, in the space-time, they are like that, you know. They are like that. So that would be L2 in time of H1, and that would be L infinity in time of L2. So you cannot compare. And you need both conditions. So our velocity has to be here. Have you understood more or less the situation? If that happens, everything is going to be well defined. Everything is going to be well defined in space, and everything is going to be well defined in time. That is going to be well defined. Well, for the pressure, there is a little problem that you again need a little bit of distribution theory if you want, or maybe distribution theory, because pressure is a function that depends on time, but you don't have the time derivatives of pressure at all. So you don't have the time derivatives of pressure. So the space where pressure has to belong is something that you have to choose again. In fact, this is not a real problem because the time dependency of pressure is absolutely irrelevant since you don't have to take the derivative of it. Here I have written a certain space for the pressure that is L1. Let's assume that it is at least integrable, but you could assume less than that. In fact, in most cases, the correct thing would be to take the pressure as a function that is just a distribution in time with values in L2. So you know that D, this script D, stands for the space of distributions. Okay, so this is sometimes a little bit too technical, and I prefer to write L1. But in fact, the correct thing would be to write the space of distributions. Does anybody know what is the space of distributions? No, you have never seen that. You have seen a little bit about this, right? You know that, I mean, the distributions, either if you want to study them, that requires time, okay? That requires some analysis. If you want to use them, it's easy, you know. The delta function, for example, is not a function, it's a distribution, so on, the derivatives of the delta function, and so on. The distributions are the dual, the distribution in time, or whatever, is the dual of the functions that are set infinity in time, is the dual of this space, the duality standing for the integral, but the problem is, the only difficulty is that the topology used in that duality is not the standard one, okay? So it's a duality, that is easy. The problem is that the topology behind the space of distributions is not trivial. And you that have studied distribution, do you know why the reason that topology requires some technical development? Why is that topology, which is the characteristic of the topology of distributions? Distributions are meant to give sense to derivatives of any order. I mean, it doesn't matter whether the function is differential or not. Distributions are meant to give sense to derivatives of any order of any function. That's the objective of distributions. And therefore, the problem of that topology is that it has to be such that derivatives are continuous. You know, so that's what makes things a little bit technical, I would say. Anyway, so I have spent some time to explain the spaces where the functions have to belong. So if you want, you can replace that by the space of distributions, a distribution in time with values in L2. I have spent some time because there is a little confusion even in the scientific community about the existence and uniqueness of solutions of the Navier-Stokes equations. I will talk about that. Well, existence of solutions was proved by Leray when omega is the whole space with appropriate decaying conditions at infinity, and in a bounded domain by Hopf in not that long ago, you know, in 1951. So the solution to that problem exists. Okay, in those spaces, the solution exists to that problem. Okay, so that's nice, good starting point. The solution exists. What about uniqueness? What about uniqueness? In R2, the solution is unique. The solution is unique in R2. And, you know, here is where the technicality comes. And if the data are such that the solution is a little bit more regular than expected, the solution is unique. What does that mean? You see, we have said, look, this is the space where the solution has to belong. This is the space where the solution has to belong. If we were able to prove that either this, instead of being H1, is H2, you see, we could increase the regularity in space, keeping the regularity in time. Or, in that argument, we could prove that U is L4, instead of L2 is L4. If we could prove that, the solution would be unique. Those solutions that are a little bit more regular are called classical solutions. Okay, this is a little also not a very appropriate name, but those are called classical solutions. Pardon me? Yes, you belong to the space that we defined before. V is the space defined before. So V is the space that V is the space that we defined there. Okay, V is the space that we defined there, and Q, as usual, V is the pressure velocity space, and Q is the pressure space. So now I'm saying that apart from being in V, we increase a little bit the regularity in space in the L2 space in time, or we increase the regularity when we have L infinity in time, then the solution is unique. Well, but there is an open problem, and this happens if t is small. There is an open problem. Uniqueness in the original space, that is where the problem makes sense, is an open problem. Or there are two versions of that open problem. The first is to prove uniqueness in the original space where the problem is well defined. That's open. That's not proved yet. And the second question is, if we want to consider solutions in that space because we have a small data or smooth data, so f and u0 are smooth, so far it's possible to prove that that the solution remains smooth for t small. Okay, for the time small. So the other open question is, would it be possible to prove that the solution remains smooth when t is large, when time evolves? So those are the two versions of the same problem. Okay, this is one of the open problems for which the Clay Institute offers $1 million reward to the person that proves that. I mean, both questions are closely related. I don't know if you have heard of Hilbert problems. So this is one of the remaining Hilbert's problems. Okay, Hilbert was a mathematician working, well, the one who designed or who introduced Hilbert spaces, worked in the beginning of the 20th century, and he posed roughly 100 problems. Okay, of those 100 problems, there are only 6 remaining. Okay, or 5. That depends. There is one still under debate. Okay, so there are, and this is one of the 5. Okay, this is one of the 5 problems that is still open: the existence and uniqueness of solutions of the incompressible Navier-Stokes equation. But this, in this sense, in this sense, it's not that it's not known anything. No, it is known that solutions exist in the correct space, and that are unique if the solution is regular. The problem is that it is not known whether in the original space the solution is unique, or whether regular solutions exist for all time or for large time. Okay, so that is what is open. Anyway, now what is known about the regularity of the Navier-Stokes equations? Well, not much. Yes. Yes. That was proved by Hopf. That was proved in the case of bounded domains. You mean? The case of bounded domains was proved by Hopf. Okay. Yes. The existence of solutions. Yes. So Leray. By the way, the proof by Leray is not very difficult. The proof by Leray is not very difficult. The proof by Leray is classical proof. Is regularization as usual, to make things smooth and guarantee that the solution exists and is unique, just Cauchy's theorem of ordinary differential equations, and then take the limit. And that regularization is done through a convolution. You know what convolution is. So the way to regularize a function very often is to convolute that with a smooth kernel. And that's what Leray does. In R3, in the whole space, this is perfectly possible. This is perfect. So you have a smooth solution. You apply Cauchy's theorem for initial problems. Cauchy's theorem is 300 years old, or 250 years old. 200 something. You apply Cauchy's theorem, not even Picard's, which is a little bit more elaborate, and then you guarantee the solution of the regularized problem, and you take the limit, and everything is more or less easy in R3. In bounded domains, it's a little bit more. Well, it's a Galerkin method, in fact. What you use. Okay. So what else is known about regularity of the solution? What else is known? Where is my pointer? Oh, here. Well, so among the possible, since we know that there exist solutions, the problem is how to fix which is the correct one. Okay, which is the correct solution to give uniqueness. So from physics, we know that solutions have to satisfy a certain property, which is given by the second principle of thermodynamics. It's a sort of entropy inequality. Okay, so the entropy cannot grow. That's the idea. So based on this concept, Scheffler, not that long ago, 40 years ago, defined the concept of suitable solutions. What is a suitable solution? A suitable solution is one that satisfies this inequality of all the possible solutions, because we know existence but not uniqueness. Of all the possible solutions, we consider those that satisfy this inequality. Why? Because this is in fact a sort of entropy inequality. Okay, that's a sort of entropy inequality. And then, if we have a suitable solution, what is the set of singularities? The set of singularities is the set of points in the space-time domain in which the function is not bounded in any neighborhood of that. So those are singular points in which the solution is not point-wise bounded. Okay. Well, the most important result that we know nowadays, that dates back to 1982, so it's the most important result that we have, is that if the data are regular enough, the Hausdorff dimension of the set of singularities is smaller than 1. So this is the best we know. It's not much. Well, there are many more results, but this one is the strongest. Okay, there are many more results, but this one is the strongest. And what does that mean? Well, it means that, first of all, if the set of singularities were 0, or where the empty set, that would be great because we would have smooth solutions. Okay, so we could be able to have a smooth solution because we are considering here the smooth solutions. We could apply the previous result and say that the solution is unique everywhere. Okay, that would be great. But the set of singularities is not the empty set. It's not the empty set. There are singularities. So next to empty set, what is the best situation? I mean, if you have a set in omega times the time interval, so it's something very, let's say, intuitive to understand. So if that's not the empty set, what is next to best? What? Next to best would be isolated points. Okay, next to best would be isolated points. So there are singular points, but they are isolated. That would be the next to best. Okay, and now if we think classical in a classical sense, we think okay, points are not isolated. What would be the next situation? Points, the singular points form a line, a curve. Okay, which is the dimension of a curve seen as a manifold? If you look at the curve as a manifold, its dimension is, which is the dimension of a curve. If you have a curve, the dimension of a curve is, no, the dimension of a curve is 1. The tangent space to a curve has dimension 1. The dimension of a surface is 2. The dimension of a volume is 3. Okay, so if we think classical, then we would like S to have to be the empty set. If it's not the empty set, to be isolated points. And then we could think, if they are not isolated points, the singular points form a line, a curve. And that would have dimension 1. If the isolated points form a surface, that they would have dimension 2, and so on. Well, it turns out that that set is such that points are neither isolated nor forming a curve. So it's a situation in between. So it turns out that the Hausdorff dimension, I don't know if you have heard of the Hausdorff dimension. So the dimension of a vector space is always an integer, but the dimension of a set may be a rational number, in fact a real number, okay? And it's defined, it's one of the so-called, I don't know if you have heard of that, sorry, it's one of the so-called fractional dimensions. There are several. Have you heard about fractal dimensions? Well, fractal dimension, anyway, it's just a way to define the dimension of a set. It's constructed, it's based on constructing neighborhoods of each point and looking at the dimension of the accumulation point of the neighborhood, anyway. So that's the best result we have, which is due to Caffarelli, Kohn, and Nirenberg. Caffarelli is a very good mathematician. That definition, that is a mathematical definition, but comes from physical inspiration. That's what entropy inequality. So, I mean, but Scheffler realized, that's a nice paper. I read it because it's nice and it's not difficult to read. So, it's that condition is the appropriate entropy condition to guarantee uniqueness in the case of the Navier-Stokes equations. That means that the set of points in which the solution is singular is small. Oh, that means that the solutions of the Navier-Stokes equations may violate that this regularity. The regularity satisfying that, the solution satisfying this, suitable solutions satisfying that may be non-regular. If they satisfy the entropy inequality, they may be non-regular only at the very isolated spots. So we are close to uniqueness, close but not there. Okay, because as I said, if that set is 0, is the empty set, we are done. I mean, the solutions are in L infinity, and in L infinity we have said that there is uniqueness. By the way, that would be L infinity in space-time. So that would be not L infinity in L2. That would be L infinity in L infinity. Okay, so that would be even more than what we asked. Anyway, well, that's the best result that we can have. So that's the mathematical situation. The mathematical situation is that the solution exists. We cannot prove it is unique. We hope it is unique. In fact, there are people that think that it is not unique. But should I break? Okay. Okay. So let's talk about the physical behavior in terms of the Reynolds number. What is the Reynolds number? The Reynolds number is the most important number in fluid mechanics, of course, and it's the following. I mean, that comes from making the equations dimensionless. I mentioned in the beginning that the original equations, when obtained from continuum mechanics, are those. Those are the equations obtained from continuum mechanics, where mu is the dynamical viscosity and rho is the density, okay? So the point is that you can make these equations dimensionless. Well, first you can divide by the density everywhere. You can make these equations dimensionless by defining u prime, the dimensionless velocity, as u divided by a characteristic velocity. X prime equals to x divided by a characteristic length, and then time. I never remember time. Time has to be the time prime has to be time divided by viscosity and multiplied time times viscosity. Let me say. So this is time by viscosity and divided by length squared. Okay, that's the way to make the equations dimensionless. Okay, good. If you do that change of variables, what you get is this: the time derivative with respect to the dimensionless variables, everything dimensionless, minus 1 over a certain number, Laplacian, the dimensionless Laplacian of u prime plus gradient prime of p prime. So everything dimensionless, where the Reynolds number is UL divided by nu. So a characteristic velocity multiplied by a characteristic length divided by the viscosity. Of course, this is the first thing that you have to take into account. The way to choose that characteristic velocity and that characteristic length is not unique. So given a problem, you never know which is the Reynolds number, okay? So somebody has to tell you which is the characteristic length that has been chosen and the characteristic velocity that has been chosen. Okay, so the Reynolds number is the most important number in fluid mechanics, which not only in incompressible flows, but also in compressible flows. There are other numbers, but that is the most important one. So how does the solution behave when you increase the Reynolds number? Behave in the long term when time tends to infinity. So there are, from the physical point of view, there are 4 stages, 4 situations. The situations are the following. First, the solution converges to a stationary solution. So when time tends to infinity, the solution converges to a solution that does not depend on time, a stationary solution. That happens for small Reynolds numbers, okay? Another possibility is that when the Reynolds number increases, the solution converges to a periodic state. That happens with Reynolds numbers larger than here, than in stage 1, but not very large yet. The third stage is the one in which the solution converges to a quasi-periodic flow. What does a quasi-periodic flow mean? It's a flow in which the solution has several frequencies alive. So it's a state in which there is more than one frequency alive, maybe 2 or 3 or 4 or whatever. And finally, it may happen that the solution converges in time to a solution which has a continuous spectrum. So all frequencies are alive. I will show that what it means in a minute. Or, from those of you that know a little bit of dynamical systems, the Poincaré sections have dimension, Hausdorff dimension greater than 1. Anyway, this is a concept from dynamical theory. But the dynamical systems theory. What is the idea? That has to be well understood because that is the essence of for simulating incompressible flows. Imagine you have an obstacle, a cylinder or whatever, and you have the flow over a cylinder or an obstacle. You have a flow that goes there. If the Reynolds number is small, then at the end you will have a steady state solution. So that I am plotting the streamlines here. I am plotting the You may have vortices. You may have vortices. So what is a vortex? A vortex is a pattern, a flow pattern in which the streamlines are closed. Okay, that is a vortex or have curvature. So you may have a pattern like that. That may happen for a small Reynolds numbers. If you increase the Reynolds number, what happens? It happens that the solution is not stationary anymore, but oscillates, has a periodic pattern, a periodic behavior. Okay, so there is a periodic behavior. Okay, that happens very often. Now, in that case, let's take a point. Boom, let's take that point to understand the physics. And let's look at one of the variables at that point in time. One of the variables, I said the velocity, but could be the pressure, could be the energy, could be whatever. Okay, and let's plot the spectrum here. That means we Fourier transform that signal. We Fourier transform that signal, and we plot the frequency against amplitude. Frequency against amplitude. Let's call it A. What do we observe here? Since it tends to a steady state, the solution, let me use colors, the solution would be just one amplitude associated to a zero frequency. That would be a steady state. Okay? In that case, how is the solution? If we plot the solution in time, we see a periodic behavior. That's the second situation. If we Fourier transform that signal, what will we have? We will have, of course, the constant associated to the zero frequency, which is the mean amplitude, let's say, plus another amplitude associated to a certain frequency. So that would be the Fourier transform of that case. That is a periodic solution. If you further increase the Reynolds number, you could have a discrete spectrum with several solutions alive, several frequencies alive. So you could well have something like that. Something like, so you have a signal that is like this, whatever, signal like that, and then there could be several frequencies alive, not only one, but several frequencies. That's a quasi-periodic flow. And finally, there is a situation in which all frequencies are alive. If you plot the spectrum, it's not anymore a discrete graph, but it's a continuous graph. All frequencies are alive, all of them. Okay, all frequencies are alive. This is, in terms of dynamical systems, the solution is chaotic. It's chaos. Okay, and there are several ways to define chaos. One is to have Hausdorff dimension greater than 1. So, and the other, well, that's something. Poincare sections with Hausdorff dimension greater than 1. And the other, which is more intuitive and more interesting in fluid mechanics, is to define chaos as the situation in which a solution has a continuous spectrum. All frequencies alive. So you cannot distinguish between frequencies because they are all alive. So the solution, if you plot the solution in time, is completely chaotic. Okay? It doesn't matter which frequency you choose. All frequencies have a certain amplitude. Have you understood the situation? This is what in fluid mechanics is called turbulence. Okay, that's a way to define turbulence. So can I go ahead? Is it not finished yet? Yes or no? Okay, I'll go ahead. Okay. How do this, let's say, this happens? The steps from 1 to 2, from 2 to 3, and from 3 to 4 happen because of successive Hopf bifurcation. I don't know if you know what the Hopf bifurcation is, but the bifurcation is a situation in which the solution is not unique anymore. It's not unique anymore, but not unique in the sense that you need not So what we have been talking about uniqueness, the solution we expect to be unique given the exact initial conditions and forced terms. So if we know the initial condition and the forced term, then the solution has to be unique. Another thing is, we are at a given time, as time is almost infinity, so we have in the long-term behavior, we are at a given time, and we wonder whether there is a unique solution or not at that time. The solution may be unique or may depend on the initial condition. You understand what I mean? So when here in bifurcation theory, when people talk about non-uniqueness, it's not that the solution is not unique if you know exactly the initial and boundary conditions. No, it's that the solution at a certain time depends on the boundary conditions, and if you perturb a little bit the initial conditions, you change the solution. That's what it means, okay, bifurcation. So you change a little bit the initial conditions, and you change a lot the solution after a while. So this is usually represented in a diagram. Well, that's bifurcation, okay? That happens also in ordinary differential equations. You have probably seen that. So usually you could plot the solution, let's say the space of the solution, which is it's a very complicated space, of course, in terms of the Reynolds number, just a representation. So for all Reynolds number, there exists a unique solution, in the long term, I mean, okay? And then all in a sudden, you have a bifurcation. What does it mean that we have two solutions for the same Reynolds number? We have two possible solutions. It means that the solutions depend on the initial condition. Of course, we will go through one path or through the other path, depending on the initial condition. Okay, you understand what I mean? The problem is that one of these solutions is usually stable and the other is unstable. What does it mean? It means that, for example, from one initial condition you get that, but if you perturb it a little bit, you switch to the other condition. That means that this one is unstable and this one is stable. And there are many successive bifurcations, okay? So the dynamical behavior of the Navier-Stokes equations is very, very complex, okay? Very complex. So the steps from 1 to 2 and from 2 to 3 and from 3 to 4 are a consequence of successive Hopf bifurcations in time. So in the eigenvalues cross the imaginary axis. Well, now the important thing is what happens in case 4. Okay, let's consider case 4, turbulence. Let's consider case 4, which is turbulence, which is written here. And instead of plotting the spectrum in time, what I have written here to explain the situation is to plot the spectrum in time, let's define the spectrum in space of the kinetic energy. So what is written here is the spectrum in space of the kinetic energy. What is the kinetic energy? Essentially the L2 norm of the velocity up to the density, okay? The energy per unit volume, by the way. Kinetic energy per unit. So this is the L2 norm of the velocity, and since you know that the L2 norm in the real space is equal to the L2 norm in the transformed space, in the Fourier space, so that's the L2 norm of the Fourier transformed velocity, but in space. So that's the Fourier transform in space. So that's why instead of frequency omega, I have written here the wave number k, okay? And since the wave number is a vector, here you consider all wave numbers that have the same norm k, okay? So L would be the wave number, vector, that would be the vector wave number, and that would be the scalar k, which is the norm of the wave number. So this is an energy, okay? So, okay, so let's take the Fourier transform of the energy, of the kinetic energy in Fourier transform in space, okay, in terms of the wave number. So for xt, for a fixed t, we have the energy in terms of the wave number, of the modulus of the wave number, okay? So for each time t, we have the kinetic energy in terms of the wave number. What I have said in time also happens in space. So the spectrum in space is also continuous in this case. This is what is called ergodicity property. But anyway, that is true. Just it's a physical fact that it is true that the spectrum happens to be continuous because turbulence is a physical phenomenon. Okay, so it's nothing mathematical. Okay, it happens that the energy spectrum, remember that we are here in the fully chaotic flow in turbulence. Okay, we are in the turbulence situation. that spectrum has, one can distinguish 3 different regions in that spectrum. If we have small wave numbers, then the spectrum corresponds to the macroscopic flow patterns. What does it mean? The big vortices. That means that the spectrum is given that will depend on the boundary conditions, the forces, and so on and so forth. Okay, so depending on the flow, of course, on the geometry, you will have one spectrum or the other. You will have something, one thing or the other. However, when k is very, very, very large, it happens that diffusion, even if it is small, viscosity plays a role. Viscosity begins to dissipate the flow scale. So there is, let's say, there is friction. Because what does it mean, small wave numbers? You know that the wave number is proportional to the inverse of the length scale. So the wave number is 1 over length. So small wave numbers means large length scales. Okay, small wave numbers means large wave length scales. So for large length scales, the flow is driven by the body forces and the boundary conditions. For large length scales, which means very small wave numbers. For very large wave numbers, which means very small length scales, very large wave numbers means very small length scales. Even if viscosity is small, it is acting. It is acting. That viscosity is acting, and it's a sort of friction. And you know that the effect it has is to decrease energy, so to make things slow down until they stop, right? So there is a region, and the important thing is that there is a region in between the large scales and the very small scales. There is a region in which only by dimensional arguments one can show that the energy has to behave as proportional to the wave number to the power of minus 5/3. This is extremely important in fluid mechanics. Okay, in the analysis and simulation, also the numerical simulation of incompressible flows, it is very important to know that. Very important. This is the so-called Kolmogorov energy cascade. Energy has to decrease with a power of minus 5/3 in terms of the wave number. Okay, you have to keep that in mind every time you perform a numerical simulation of a turbulent flow. Okay, so that was derived by Kolmogorov, who was a mathematician, as you know. I mean, that's physics, we could say. But Kolmogorov is the same mathematician that did a lot in functional analysis and a lot in probability theory and a lot in many other things, also a lot in fluid mechanics. So that's how the spectrum looks like. So the spectrum has, in the energy in terms of the wave number, has 3 clearly distinct regions. One in which you don't know what happens. I mean, so the energy is driven by the external forces and the boundary conditions. Another one in which dissipation takes place because of viscosity. So viscous effects dissipate vortices. So there are not very, very, very small vortices cannot exist because there is a point at which dissipation kills them. And then there is this inertial range in which the relationship between energy and the wave number is k to the power of minus 5/3. So if you plot it in logarithmic scale, so that's the logarithm of the energy, not the energy, but the logarithm, but that's a log scale, then the slope is minus 5/3. Okay, and this happens, and it is surprisingly precise. If you ever simulate a turbulent incompressible flow, incompressible, by the way, incompressible flow, you will observe, if you have a good code, of course, if you have a good code, you will observe that slope. Of course, not exactly. This is an idealization. You will observe something, you know, of fluctuations like that. It's not perfectly a perfect line. I'll show an example, I guess, where you will see that spectrum. You could plot. You could do the same in pressure. Pressure against frequency. So the Fourier transform in time also behaves like that, but with a slope minus 5/3. I'll show that in one example, I guess. No, in one. Yes, in one. But in one of the application parts. Okay, so that's it. We are done with the theory. Okay, everything I've said is about the statement of the problem. I said at the beginning that it would take us a while, 1 hour, more than 1 hour, to state the problem. Okay, so those are the Navier-Stokes equations. Good. So let's now that we know them, let's first see something easy. Let's relax and introduce the time discretization first. Time discretization of the Navier-Stokes equation. So I mean, of course, we are interested in doing numerics, and therefore we have to discretize in space, we have to discretize in time, and we have to linearize because this is a non-linear term. Okay, the convective one. But that's easy. That doesn't introduce anything else. So what I will recall here is which are the most important time integration schemes used for the Navier-Stokes equations. Okay. So let's write the problem in this way. So we have to obtain the velocity and the pressure solution of this system. And now I've written the convective term as n of u the convective term, and L the viscous term, which is the Laplacian. Okay. So this one is linear, and this one is quadratic. This is u gradient of u, and this is linear. Okay. So the notation I will use is the following. I will use a superscript to denote the time level. That's we consider, of course, a partition of the time interval. And delta t is going to be the time step size, constant to simplify. Of course, everything can be done with variable time step, but let's assume it's constant. So the increment of a function in a certain time step is denoted delta f. That's just the increment of the function, where the superscript means that that's the function evaluated at time step n, and we hope it will be an approximation. We hope it will be an approximation to the exact function at time tn. Okay. As usual, we also denote fn plus alpha, the convex combination of fn plus 1 and fn. So convex combination means this. Alpha is a parameter that varies between 0 and 1. So this is what fn plus alpha means. And finally, delta t of fn is the increment of f divided by the increment of delta t. So this is going to be an approximation to the time derivative. Okay, this delta t. So that's notation. And here we will see discretization in time using monolithic schemes. Monolithic means that we try to solve for the velocity and the pressure at the same time. Okay, that's what monolithic means, in contrast to fractional step that we will see later. So let's talk about one-step approximation to the time derivative. What is a one-step approximation? A one-step approximation is the one in which you only use values of the unknown in one step. So we have, suppose that time is here, time, and we have our unknown u that will depend on position but also on time, and we partition the time interval into time steps. So as I said, the size of the time step is delta t. If this is n and this is n plus 1, the value of the function here will be denoted un plus 1, and here the value, whatever it is, will be denoted un. And this is a step, okay? So single step or one-step approximations means that we only use the values of the unknown in one step. So here and here to compute the approximation, okay? Maybe we may use other values, but those are called multi-step, okay? I will not talk about all possibilities, but so which are the most common ones? The first is so what will we do? Here we replace the time derivative by the incremental quotient. We evaluate somehow the convective term. That changes. If we want a single step approximation, the viscous term is always approximated using the value at un plus alpha, this convex combination of un and un plus 1, and pressure is always evaluated at n plus 1. The right-hand side at n plus alpha, and the divergence of u at n plus 1. Why am I evaluating the pressure always at n plus 1? Because in fact, it doesn't matter where you evaluate the pressure. It doesn't matter at all. Why? Because what matters is that here you have the gradient of a certain scalar function. It doesn't matter if it is n plus 1 or n plus 2 or n plus whatever. It's just the gradient of a function. Since the pressure does not have any time derivative and does not appear anywhere else, the pressure here can be identified with Pn plus 1 or Pn, whatever you wish. Okay? So sometimes there is a misunderstanding that people call it, oh no, n plus 1 half. No. I mean, it doesn't matter where it is. Okay? It's just the pressure. And likewise, the divergence of the velocity, where has to be enforced, the divergence zero condition. Okay, if we assume that at time n, the velocity is divergence free, we only have to assume it at time n plus 1. It doesn't make sense to impose that at n plus 1/2, because if divergence of un is already 0, the only thing we need is that divergence of un plus 1 is 0. Okay, so these two terms are evaluated at n plus 1, so where we are looking for the solution, but that one doesn't matter where it is evaluated. Okay. So this is un plus alpha, this is clear, but what about the convective term? So for a first order scheme, if we only want to be first order in time, what does it mean first order in time? It means that the solution u minus the exact solution is of order delta t, the time step size is bounded by delta t, okay? Just delta t, not delta t squared. So for a first order solution, the simplest way is to take alpha equals 1, so alpha equals 1, and then either the convective term evaluated everything at n plus 1, which is the most advisable option, or evaluated at n, at the previous time step, or evaluated the advection velocity at n and the transported velocity, so the second argument at n plus 1. So let's see. First, if everything is evaluated at n plus 1, this is clearly the backward-Euler method. I suppose you all know that, right? The backward-Euler method. So that is the incremental quotient, is un plus 1 minus un divided by delta t, and everything is evaluated at n plus 1. So because we are taking alpha equal 1. No problem with that, right? If the advective term is evaluated at n, so at the previous time step, what happens? That means that we are taking the convective term explicit. Explicit, you know, that means that is known already. So we evaluate the convective term here. Okay, we evaluate the convective term here at the previous time step. And you know that leads to a stable scheme only if delta t is small enough. So I'm assuming that you all these concepts about integration are known, you know. Do you know them? Do you feel comfortable with them? Do you want any further explanation? So it's all okay, right? Okay. So in that case, in case in which you treat a certain term explicitly, you need a stability condition. So the time step size has to be small enough. Okay. Whereas in the other case, the scheme is unconditionally stable, which means that any delta t, any time step size leads to a stable scheme. In the case of incompressible flows, there is a curious case. It's that the one in which you take one of the components, one of the velocities explicitly, and the other one implicitly. And the resulting scheme is nevertheless unconditionally stable, although this is very dangerous. Why is it unconditionally stable? It's easy to prove. Because in the weak form of the equations, we haven't seen that yet, but I just anticipate. The weak form of the equations has the convective term. Okay, that's the convective term. To prove stability, we take the test function equal to the unknown, but the unknown is un plus 1. Okay. If we take v equal to un plus 1, it happens that that integral is equal to what? I mentioned that yesterday in the context of the convection diffusion equation. What is this integral equal to? When this is a velocity, if this velocity is divergence free, it can be shown that the convective term is skew symmetric. That integral is equal to 0, because if you have in a skew symmetric form, you have the two arguments equal, the result is 0. Therefore, even if you treat that term explicitly, it doesn't harm. It doesn't harm. Okay, so you can treat explicitly. This term is 0. It does not destroy stability. But this is very dangerous at the numerical level. When you do numerics, that is not 0 point-wise. The divergence of u is not 0 point-wise, and you may get into trouble. Many people use that, by the way. It is possible, and sometimes it works, but it's dangerous. Okay, it's dangerous. Have you understood the argument? No? What do you want me to repeat? So, do you understand that this is 0? Yes. When you prove stability, since this is 0, it doesn't matter whether you evaluate that explicitly or implicitly. So that can be evaluated wherever you wish, because since if the divergence is 0, you can evaluate it wherever you wish. This is 0, so it will not affect the stability. That, of course, matters because that is 0 as soon as this argument is equal to this 1. So that really matters. It is important to treat that one implicitly. That one needs to be treated implicitly, but that one doesn't matter. However, this relies on the fact that the divergence of the velocity is 0. And in the numerical approximation, that will not be exactly 0, but only in a certain weak sense. And in fact, point-wise, it will not be 0. Anyway, okay, so those are the first-order schemes. What about second order? For second-order schemes, you know that the most classical choice is to use Crank-Nicholson approximation, which means that you take alpha equals to 1/2. So, in particular, in the viscous term, here you evaluate it as 1/2 of the viscous term at n plus 1 plus 1/2 of the viscous term at n. Do you know the Crank-Nicholson scheme, right? You all know that. Okay, that's Crank-Nicholson. And in the case in which you take alpha equal 1/2, where do you compute the convective term? So you have two choices. The first choice is to take the convective term also using Crank-Nicholson. So that means that you take the convective term at un plus 1/2 everywhere. Okay, that's the first choice. But what's the problem with this choice? The problem is that the scheme is nonlinear, of course, because you have that nonlinear term. There is another possibility. The scheme that results in that case is unconditionally stable for Crank-Nicholson. There is another possibility which consists of taking the advection, the convective term, explicit. But you wanted to have it second order. Okay? So you wanted to have it second order. And you want to use only known values of the convective term, only known values of the velocity. So if you want to have it explicitly, if you use this term, of course, you will only be first order. Okay? So which is the way to obtain a second order scheme? So the way to obtain a second order scheme is to obtain an approximation of the advective term using the velocity here and the velocity here. So, okay, un plus 1, n minus 1. So you take the derivative only here. Okay, that's a single step scheme. But you use previous values of the velocity, not in the derivative. The derivative is approximated as un plus 1 minus un divided by delta t. So it's a single step scheme, but you use values of the velocity in the equation of previous time steps because you want to be second order. Is that clear? Well, that second order approximation, in fact it's an extrapolation from values at n and n plus 1, can be shown to be, the coefficients can be shown to be 3/2 and minus 1/2. This is just a simple Taylor expansion, so it's very easy to obtain those coefficients. That approximation is called Adams-Bashforth approximation. So the scheme that is obtained by using an Adams-Bashforth approximation for the advective term and Crank-Nicholson for the diffusive term, because in the diffusive term we have used Crank-Nicholson, it's called Adams-Bashforth Crank-Nicholson, ABCN. Okay, people know it as ABCN scheme. What is the advantage? The advantage is clear. The nonlinear term is treated explicitly, and therefore at each time step we have to solve a linear problem. So we don't have to iterate. Okay, we will see later how to iterate, but in that case we don't have to iterate. I would say that this is perhaps the most popular time integration scheme in CFD, definitely, particularly in commercial codes. I think there are other schemes that are better in some senses, but this one is cheap, is reasonably good, reasonably stable. It is only conditionally stable. The time step has to be small enough because we are treating one term explicitly, but is reasonably stable and very cheap. So it's in commercial codes is definitely the most popular scheme. And finally, Which is the other option, the other family of schemes? Okay. The other family of schemes is obtained by, instead of evaluating the derivative using a single step method and then maybe using other values, the other idea is to evaluate everything at time n plus 1, but to approximate the derivative maybe using previous values of the unknown. Those are called multi-step schemes, okay? Multi-step schemes. Or gear schemes or BDF schemes, backward differencing, they are also called. BDF perhaps is the most popular name. I don't know which is the name that you know, but either gear or BDF. And that is the second order BDF scheme, okay? So everything is evaluated at n plus 1, n plus 1, n plus 1, n plus 1, n plus 1 everywhere, so everything is evaluated here. But then the time derivative is not only the incremental quotient in that time interval, but also uses previous values. For example, the second order version uses un minus 1 with these coefficients. This is called sometimes the second order gear or the BDF2 scheme, okay? Backward differencing of order 2. Backward differencing of order 2. That's the BDF2 scheme. Okay, that's what I wanted to say this morning. I don't know if you have any question concerning time integration. Of course, that's not exhaustive. That's not exhaustive. I just want to make two additional remarks. The first is that there are other methods that maybe I am liking them more and more. In particular, methods based on, you know, Runge-Kutter's methods to integrate ordinary differential equations, right? Runge-Kutter. Runge-Kutter are not explained here, are not multi-step. This is a multi-step scheme. Runge-Kutter methods are called multi-stage schemes, okay? Because from you go in Runge-Kutter, you go from n to n plus 1, but instead of going from n to n plus 1 in just one shot, you do it several stages, okay? That's Runge-Kutter methods. And then Runge-Kutter, plain Runge-Kutter is, you know, but there are combinations of Runge-Kutter with multi-step that are very nice, you know, there's a family of Padé integrants. Well, that's going too far, but there are some time integration schemes that are very, very good. By the way, that one is, I would say, the most stable one, the BDF2. It's definitely more stable than Crank-Nicholson, even though both are second order. Second order means that the difference between u at time n plus 1 and un plus 1 is of order delta t squared. It's second order and is unconditionally stable, that one. That one is, both are second order, but this is more stable than the other. And the reason is that the error of the BDF scheme is in amplitude, whereas the error of the Crank-Nicholson is in phase. Both are second order, but that is more stable because it decreases amplitude. It is more dissipative, which is always good for mechanics, okay? Any comment, any question? Of course, I didn't want to talk about time integration. It's not the topic of this course, but I needed to give an overview of the time integration schemes required, okay? No questions then? Okay, so I'll see you this afternoon and we'll set the weak form of the problem and start discretizing it, okay?